Okay, so I believe that we have audio the room, but I hope that you can hear me well. So we will proceed this way. Welcome to today's workshop. Today we are going to talk about solar heat in industrial processes. We are happy to be here. We are presenting, this is the final event of Seed2Fair project. This workshop will be divided in two parts, the one starting right now at 9 o'clock and a second one starting at 10 o'clock. And we are going to present today the 5 years result of this project among some of the partners of the project. So, as indicated, we are going to start this first session. My name is Miguel Farzuela. I work at CIRCE. We are the conductors of the project, and today we are in this first slot. We are going to check the first results of the project, the tools that we have developed. We will start with a short presentation of the project. Then we'll look at the solar thermal technologies that we have used in the use cases of the project, and then we'll present two of the main tools that we have produced, which are the replication tool and the control tool. The control tool allows real-time operation of the plant to check what is the best way to inject the solar thermal energy into the industrial processes. And the replication tool is a tool that allows any industry to make a feasibility studies to know what is the best technology and also the techno-economic analysis to be implemented in the specific industrial plant. Finally, during this first workshop, we'll have the hand-on experience from Roda, which is one of the demo sites of the project. It's a winery located in La Rioja. And then in the second part of today's workshop, we'll start with the Martini Rossi solar plant. Information from their side, their experience of being part as pilot of this project. Then we'll go to the business and financing schemes of the ship installations. We'll see also the replication studies that we have developed for 10 plants around the world, in which we have assessed the techno-economical feasibility of these technologies in different industries, not only of the agro-food sector, but also in other industrial sectors. And we'll finalize the workshop, the second workshop, with some information about the renewable penetration in the Spanish industry, also the roadmap for deployment of the Seed2Fair technologies, and we'll conclude with the lesson learned and policy recommendations. So, as we are a little bit late on the start of the workshop, let me go very quick through the main information about the project. This project started in 2018 and is about to finish this month. So in the end, it was more than 5 years of development. The main goal of the project is to foster the integration of solar heat in industrial processes by developing the tools that I have already presented, and to be also a main demonstrator of the solar implementation of solar at high temperature energy in the industry. What happens today? This is just the outlook at the global energy demand. As you can see, 51% of the global energy demand corresponds to heating and cooling. About only 10% is renewable energy. In the EU, it is increasing year by year, but it's only 23% of this 51% of total consumption. Therefore, it's clear that to fulfill the goals of decarbonization that we have in the European Union and also around the world, we should increase the deployment of renewables at all levels. Here in this project, we are focusing on low and medium temperature industrial processes in which we can inject directly solar heat in the process. Depending on the scope of the temperature, different technologies are available, and some are more usable in some sectors, and some are less. The problem that we have detected that we have in this industry is that the industry is used to use steam at high pressure and high temperature, and then they lower it for their own needs. We see that for solar heat, it's better to work at lower temperatures instead of producing always saturated steam. But this is something that we learn from the demo sites today. Just going through the consortium, we are about 15 partners. We have several technology providers, as it is industrial solar or TVP solar. We have different research partners, and also the demo sites involved in the project. Mainly, as presented before, we have 4 demo sites: sugar boiling at Porto in Portugal, foie gras production, the south of French Larnaudie, spirits distillation in Martini Rossi, and wine fermentation and stabilization in La Rioja at Roda. As indicated, what we are going to see today is the presentation of the replication tool, which is the software for the feasibility studies. We'll know also about the control tool, which is the decision support system for the demo sites in order to best operate their own plants. We'll know about 2 of the demo sites. We'll know today about Roda and Martini Rossi experiences. And we'll know about also the 10 feasibility studies that we have developed for the industry. Just some big numbers. We have installed in this project more than 1 megawatt of thermal power in the demo plants, higher average solar efficiency goes from 45 to 54, while the solar fraction amongst the year of the demo sites is about 24%. As said, we are right now on the final stage of the project. So we are right now just evaluating the final results of the demo sites, and also to know what is the real experience and the payback of these installations. This is the Martini Rossi demo plant, and in the next workshop we'll know from them. So I won't use additional time, so we can move to the next speaker of today. We will be Dimitris from TVP Solar, who will present their equipment, and then we'll continue with the industrial solar. I believe we should put this on kind of close for the online audience.
Okay. The camera is.
Camera is
Okay. Good morning, everyone. Thank you for coming to our workshop. I'm Dimitris Papageorgiou. I will present TVP Solar's solar thermal technology. And before I go through the presentation, let me give you some background information about our company. We're a fast-growing small and medium enterprise that has developed, manufactures, and markets our high-vacuum flat panel technology. We are based in Geneva since 2008. Okay. And our manufacturing facility is located in Avellino in the south of Italy. Overall, we are around 180 people, and we have already demonstrated our technology in various sites, and which we operate or are under construction in 11 countries around Europe, the Middle East, and Americas. Now, this is our core technology, the so-called high vacuum flat panels. And we claim that it's the best solar thermal technology, at least in the range, the temperature range that we operate. And we have good reasons to claim this, because it's our panel is the only panel in the world that combines a planar arrangement, so flat panel under high vacuum. The envelope that you see on the bottom left is all under high vacuum, and there are several technological innovations that are behind this that made this panel so efficient. High vacuum reduces to a minimum the thermal losses, and this is why we have a higher efficiency compared to other technologies, and we can also operate in reality. Our systems deliver up to 180 degrees Celsius heat, and we are Solar Key Mark certified up to 200 degrees. Also, an important feature of our technologies is that we guarantee that there is no vacuum loss for at least 20 years. So there is no degradation, no performance compromise over the whole lifetime of life cycle of the panel. Now there are several patented technologies behind this product. They have to do with the core technology, the vacuum technology. They have to do with the system itself, the solar system, but also the manufacturing process. Here you can see two diagrams where we compare the performance of our collectors to other solar thermal technologies under two different conditions, sun conditions. Full sun conditions on the left and average daylight conditions on the right. As you can see, in the temperature range that we wish to operate from 70 to 180 degrees, we are well above the efficiency performance of other technologies like the flat panels. You can see the orange line that is dropping, is more steep and dropping because of the low, let's say, the higher thermal losses, but also parabolic collectors as well, and other collectors. What is important also to mention on the right, under average daylight, so reduced sun conditions, we still exceed in performance, but we perform even better compared to the other technologies, exactly because we minimize the thermal losses. Here in the diagram, you can see three alternative ways of integrating our technology, our systems into existing industrial processes. So in the case where there is a steam network at 8 or 10 bar, what we can do is we can preheat the return condensate and the feed water up to, let's say, 140 degrees. Where there is a low pressure steam network up to 3.54 bar, we can actually deliver steam. And what is the most, let's say, the optimal integration is directly to the processes where we can operate at lower temperature, and that means that we can deliver a higher efficiency. But this needs direct integration into the processes. And you can see on the bottom right different processes that operate in this temperature range. And of course, on top of the agro-food industry that we demonstrate in SIP2 Fair, we can serve other industries, as you can see, textile, pharmaceuticals, and chemicals and other. Now, in this diagram, you can see the solar panels on the top, and the primary circuit with the blue line, the return, and the red line, the hot water that goes through a heat exchanger to the processes. In case we have excess we produce excess heat in the solar system, this dry cooler anticipates the heat to the atmosphere, and where there is not enough solar heat or there is no solar heat, then the circuit of the client operates as it used to operate before we installed the solar system. Now, some interesting data about our systems. We target large-scale applications, so preferably multi-megawatt or even tens of megawatts of applications. 1 megawatt is around 1,600 square meters of panels, and this is translated to a footprint area of 3,000 square meters. Heat production, it depends, of course, on the climate, the conditions, etc., but it's around, let's say, for different temperatures, we will see in some next slides, around 1,300, let's say, megawatt hours per megawatt per year. Our capital expenditure for the whole solar system is somewhere below 1 million euro per megawatt, and you can see that the operational expenditures, which includes operation and maintenance, electricity, and spare parts, it's really minimum. It's 6,400 euro per megawatt per year, and we expect a lifetime of 25 years or more. Now, in this graph, you can see from different geographies and locations what we can deliver in terms of temperature. For different temperatures, what we can deliver in terms of solar heat. So this is, let's say, a map that somebody can use just to figure out very roughly what is expected in terms of production of heat over the year. And apart from our core technology, we have standardized the balance of system. So we actually provide turnkey installations based on our system design. And of course, we have a control and monitoring system that is applied for autonomous operation of the system, plus a remote control of it through our colleagues. Now, I will pass very quickly through 3-4 examples. The first one is in Martini and Rossi. It will be presented later on. The interesting thing here is that we operate in a dual mode, meaning space heating during the winter period, and from April to September, steam generation, or to May to September, I don't know. An interesting installation in Saudi Arabia is the one that you can see here, where we can deliver heat above 160 degrees, even with the panels being covered by dust. And this is really important for desertic climates. So we don't need to clean the actual panels. And this is the opposite example. In Geneva, we operate a solar district heating network, and you can see that we can deliver above 80 degrees Celsius, even with the panels covered by half by snow. And a last case is the solar air conditioning. So we couple our systems with absorption chillers, double effect absorption chillers, to provide cooling air conditioning. And we have also wrote the case today that will show us a similar example. These are the product certifications. You can download from the Solar Key Mark database our certificate, and you can see how our panels perform in different conditions. And this is my presentation. Thank you very much for your attention.
So now we move to Gaba from National Solar. In case that the audience has any question, feel free to ask after the presentation. We have some time at the end of the session. The floor is yours. The microphone is over there.
Sorry? When? When was the cooling plant commissioned, the air conditioning plant commissioned? It was commissioned, if I remember well, in 2017 or 18. So there are some years now that it operates. You're welcome.
So good morning, everyone. Buenos dias también. Thank you for the session today. I'm pleased to be here and to present also our contribution to this project. Ship to Fair was a very interesting project from the beginning, and we are glad that we are coming to an end with interesting results. We are seeing the summary of everything today. There are several deliverables. If you're interested, like in the research part of it, get in touch with the team. You can also find a lot of resources online on the Ship to Fair website. I will present today some parts, but now the Fresnel collector technology, which is what we developed at Industrial Solar. My name is Rafael Ribeiro, and I'm the R&D manager and business developer at the company. So this is what our technology is about. So we use concentration of solar radiation to produce high temperature heat. I will show some details, but basically you see here already how the collector would work. You basically have the mirrors that are moving and tracking the sun in an absorber tube, in a vacuum receiver. And with that, we have the concentration of sunlight, which then can produce the high temperature. So this is how the technology works. So for you to see this animation here, basically show it. So you have the mirrors moving with a control system that are tracking the sun. The concentration of sunlight in this pipe hits the fluid. And I will comment about the heat transfer fluids later. But interesting is that it was designed also for rooftop applications with a low weight. And the system is very modular. You're seeing here 3 modules. They're connected to each other, but they have very small footprints. So it's very suitable for industrial cases, not for CSP power plants, but actually for the industry. And that's where we are in the range that we are aiming. So the collectors, the main components of the collector, basically the mirror system, which is made of glass, silver layer glass. Also the structure, which is the lightweight structure, as you can see, he was installed in the roof in this case. The main thermos part of the collector, which is the absorber tube, which is the receiver, we call it, that receives the heat collected by the mirrors. And we have a control system. As you can see here, this is the HMI, the interface. This control system is actually the brain behind the collector operation. Interesting to mention is that all of these components, they are actually industry standards. So Industrial Solar did not develop every component itself. They basically came with a system as, for example, if you're designing a car, you basically do the same. You develop the components and then you ship them to assemble in the factory. So we do the same here in this case. All of them, they are already tested for years. For example, the absorber tube that we use is the same used in the power plants as we have several here in Spain. The 70 millimeters absorber tube, standard from the industry. The mirrors are also produced by major players, producers of glass mirrors for the CSP. And the structure is also suitable for very different environments. So I will comment a little bit different because this is also interesting for you, like how we develop a system, a design of the system. So basically we have 5 steps. The first step is what we call the initial assessment. In this initial assessment, we analyze initially the load profile of the client, and then we go to step number 2, where you do a first performance simulation. In this performance simulation, we have our own simulation tool. In Ship to Fair now, it's also possible to simulate how our collector would behave in this case. And if these 2 are green light and green light here, then it moves to the system engineering, which then is where the components are properly sized, especially hydraulic and electric systems. After that, we go to the construction and commissioning. We also develop and do turnkey solutions and implement the system on the site of the customer. And we do support for system operation with maintenance contracts. And our system is designed for at least 25 years. We have the first collectors installed in 2007, sorry. The University of Sevilla, there is one of our collectors there, if you want to have a look. It's there for a research purpose. It's already now for 15 years, 16 years. So this is how we do a project on that. What is important to assess? basically what are the temperature demand. As you have seen, it's a concentrated collector, so it's not aiming to reach 70 degrees, 80 degrees, but it's aiming for steam part or for thermal oil, for hot air above 100 degrees, typically speaking. That's what the purpose of the system. Location is very important because as we are working with the concentration of sunlight, you have seen the graph that Dimitri showed, the radiation varies in different parts of the world, and especially in Spain also. If you go to the northern provinces and if you go to the south, you notice the difference. The heat transfer fluid choice is also a very important topic, and it's very important to check the available area, especially for industrial cases. Normally they have constrained space regarding their demand. We call it the energy density, so they need a lot of energy in a very small footprint. So important to check the size, shape, and it's strange here, but the reference of area is around 3,000 square meter per megawatt installed. So this is what you see. It's a modular system that you basically connect rows with the hydraulic control system to a steam drum that then is integrating and generating steam in this example. Installation options are basically two. The ground installation, where you can see here the systems are put on ground, on concrete roots, feet, and also rooftop installation. This case here was made, interestingly, the BOP, what you call the balance of plant, is installed on top of the boiler room, and the steam drum, which is what you see, this big vessel here, is delivering steam to the main steam grid here, which is actually below where you see the chimneys here. The boilers are installed underneath. So options of integration, we basically have three options, which is the supply level. Normally is our preferred option. Depends, of course, of the size of the demand, of the distance from the collector field to the integration point. Basically, we are in parallel to the boiler. Second option is the process, so we can also connect to the process. And also we do some cases the preheating. For example, we have now cases for the ceramic industry. They need heat at, I think, 450 degrees Celsius. And in that case, we do, for example, a thermal oil system here, heating up to 350. So it's an energy saving system. So what are the heat transfer fluids that we work? I'm showing three options here because I think this is always a good question, what to do with this type of collector, this technology. So steam for the industry, I think, is the preferred option, normally speaking. Some case they also use hot water grid, but normally they prefer the steam system because steam is easy to transport. We have like small pipes. And as we don't interfere in their operation, we normally try to integrate in the same level that they supply. Advantage of steam is the low cost, the heat transfer capacity, the performance, the no contamination, and the water availability, and the risk of leakage is actually very minimal. The second option is pressurized water. For example, some breweries, they also use pressurized water, which means water above 100 degrees Celsius. Of course, water below 100 degrees Celsius is also pumped with pressure, but in this case, we call it superheated water. It's also low cost. Of course, in this case, the energy usage for the pump is a little bit higher because you need high pressure than what we have for this system. It's also this, the heat transfer performance is not that as good as the steam, but it's also quite good. And no contamination, water availability, and risk of leakage are similar to steam. And thermal oil is normally used only for systems for very high temperature. We call it the cut line above 230 degrees Celsius. The advantage of the thermal oil is the low pressure that you operate the system, low compared to steam or pressurized water. The freezing risk, which is also normally mitigated. There are some oils that would freeze below -5, but some cases they can be up to -20. It's less corrosive than steam, of course, but of course you also have the cost of the thermal oil. So for systems like that, it's important that they need this temperature really. So here's some overview of the advantages of how to use this technology. So basically the ground usage factor is one of the main advantages because it's a very compact collector type. The wind load is also very minimal. As you have seen the design of the collector in the photos, the meters are around half a meter above the ground, which means that you can have low foundation structure. You don't have to spend much on that. The weight distribution is also very well done, and the operation is automatic, so there's no interaction, or there's no need for someone to interact with the system. They can change parameters, of course, but it's not needed for starting and finishing. And also the low dust accumulation, because as a tracking system, when there is no sun, the mirrors are facing down, so there's no dust accumulation. And here are some examples of how the mirrors look. There's a bar here, but actually the stop position when the mirrors are facing down, the manual cleaning position, and also the system detects rain and cleans itself, puts in the self-cleaning position. So applications, you have seen also from Dimitri's presentation, they are similar because basically we are aiming for the low and medium temperature heat in this case. You're seeing this graph, probably have seen more times. The graph is the industry, represent 1/3 of the energy demand. Heat is the majority of this 1/3. And in this part, we have above 50%, which is the low and medium temperature. And most of these processes, they use heat transfer fluids that we also operate. So here's the summary of them. So food and beverage, for the agro-food industry, we are looking at this part specifically, but also textile, pharma, paper, automotive, oil and chemical, and different processes. And with that, I close my part. I thank you for the attention, and I'm also open for questions.
Thank you very much, Jaguar. The question? In the recent years, we saw that the natural gas, that was the main source for the industry figure, changed a lot the prices. In that time, in the recent years, it's a question also for both of you. Did you experience an increased demand for this kind of solar systems? And right now, that the natural gas price is again at its previous value, has this impacted again on the demand? So what's the situation that you see from the changes of the natural gas price in the recent years?
So I can start then. I think we experienced a very high increase in interest. It's interesting because most of the companies, they already contacted us in the past, and then they come back again because they realize that, oh, that can be a solution for me. The challenge is always to reach a high solar fraction, and I think that's the problem for all solar technologies in general. But we managed, for example, last year to close several engineering contracts, which is the first step, step three that I mentioned from the project development. And we are closing turnkey projects this year. So I think this change last year really impacted positively our development. This year still, I cannot say that the interest reduced because after the pledges for carbon reduction, these companies from last year, they still have to do something now, even if it's for greenwashing or for whatever reason. But they still are coming to us, especially the big corporations. We are also aiming the same megawatt system sizes, and I think they are still keeping their interest. We have to see if this impact next year development, but for this year, I think we are good.
I can also confirm what Irapa just mentioned, the higher, let's say, level of interest from industry, for sure. It remains there because it's not only that it was initially, let's say, raised due to the higher prices of natural gas, but there is also still the concern of the energy security. So companies have now a longer term perspective, so they don't see just in the short run that the gas prices have come down, but they would like also to see and plan for the longer term, especially when the volatility of the fossil fuel prices is quite high. And also, at least to my understanding, their commitment to decarbonization grows stronger day by day because of also the push from policy makers and local communities and societies. From our perspective also, we saw an increase in demand for solar district heating. So we operate also in the lower, let's say, temperature range of 70, 80, 9 degrees. And this is a major market, especially in Europe.
Okay, thank you very much, all of you. This is there is an increasing appetite, so with past situations, we get some good news. Continue with the agenda. Next item will be the presentation of the control tool, which was going to be presented by Victor Roberger from West. Fortunately, he cannot make it to Madrid, and I'm going to check
My name is Victor.
hear him, this is correct. So we'll hear a short introduction and live demonstration of the control tool, and then I think that we'll move to the experience from control.
Unterberger, I'm from BEST, which is an Austrian research center and which stands for Bioenergy and Sustainable Technologies. Unfortunately, I cannot be here today with you, but I'm happy to give you a short presentation regarding the ship-to-fare control tool. Starting with the goal of the control tool, the goal is to optimize and improve the integration of solar heat into industrial processes during operation. So the replication tool, what you will hear about later on, is for designing or set up the optimal design of a solar heat for industrial process. And then when it is built, it's about controlling the tool, it's operating the tool. And this is the goal of the control tool, to optimize it during operation. And here, regarding low-level control aspects, like the control of the temperature, for example, through high-level optimization of the whole system, like optimizing the whole system process as well as solar thermal plant, and to up to adding artificial intelligence techniques for fault detection and forecasts. So this is the goal. How is it the design? The design of the tool aims to be as flexible as possible in order to be applied to a multiplicity of systems, depending on the user needs. So what do the user needs? For example, does the user need a better control of the solar thermal plant and optimization of the whole system? Depending on the plant design, so which heat producers are available, are there storages available, and finally also depending on the level of automation. Are there many sensors available? Are they digitally recorded? Can the sensors be used in a control strategy? So this is the design. And in order to be as flexible as possible, the control tool consists of a framework of 6 modules, which allow to make the most of the solar heat production. And these models are deals with different control topics, different control challenges. And the first model A is about the control of the solar thermal plant. The model B is about the control of the integration of solar energy into the plant. The model C is split into a model C1 and a module C2, which is in both cases the optimal interaction on plant level, either by rules or by an MPC, a model predictive controller. I will go back to the tool, to these modules later on to explain some of them in more detail. And furthermore, model D is about forecasting methods, and model E is about distributed learning features, and finally, model F is about the calculation of key performance indicators. And depending on the level of automation existing at the plant. So if you have a low level of automation, less sensors, manual readings, up to a very high level of automation, like many sensors, digital recorded, the different modules can be applied. And these are then chosen based on the possibilities on site and the user needs, and the chosen modules like A, B, C, D, E, F form then a specific control tool for a plant. So not all of them have to be applied, but some of them in case what the user needs and what are the possibilities on site. Now I want to give you just a little more detail about the modules, on which part of a system they are working on. So if you consider a general system where we have an industrial plant, industrial plant where there's maybe a combined heat and power unit, a thermal energy storage. Then we have the solar thermal plant, which is maybe integrated over 2 heat exchangers for high temperature and middle or low temperature. And then we have weather forecasts available on site to tell about the weather of tomorrow. And this model A, this is about the control of the solar thermal plant, deals only with this part of the plant with the goal to provide a stable outlet temperature of the collector. Model D is combining or is considering the solar thermal system and weather forecasts in order to provide the future heat forecast. So how much how much heat will the collectors produce in the future? Model B is about the control of integration of solar energy into the plant. So it's about the stable hydraulic conditions. Model C considers the whole system and is about the optimal interaction on plant level. And has the goal to have an optimal overall control. Similar with the Model E, distributed learning features, it also considers the whole system and has the goal to provide an efficient and smart monitoring. And finally, Model F is about the calculation of KPIs so that you know how are the key performance indicators at your system. Now I want to go into a little bit more detail of the different modules. We don't have time to explain all of them, but some of them I want to go a little bit more into detail. Starting with Module A, the control of the solar thermal plant. So typically when we have a plant, we have the hydraulic conditions and the thermal conditions. And if we measure the temperature, we want to compare it to a set point, so to a desired temperature level. And if they're not the same, we receive a temperature error. And this is then handled in a temperature controller, very often an on-off controller, which then controls the pump in order to provide a certain outlet temperature of the collector. Within the Model A, we substituted this temperature controller by a primary proportional integral controller and added an anti-wind-up procedure in order to handling the temperature. And furthermore, we added a thermic feed-forward control. This feed-forward control is considering the solar irradiance, the ambient temperature, as well as the set point, and already calculates the desired flow for steady-state conditions, which is then added up by the output of the PI controller. So this gives us the desired flow we want to have in the solar collector, and then we have a secondary PI controller also added, updated with an anti-wind-up procedure in order to handling the flow rate. So it's a cascaded structure. Coming now to an exemplary explanation of Model D. So here in the lower part, you see on the x-axis a week starting with Tuesday, and on the y-axis the solar radiation, the global solar radiation in watt per square meter. And you see it is very high, then it drops down, so it's a very cloudy day here, and then it goes up again. Quite typical very typical. Then here we see the same x-axis, and on the y-axis we see the heat output of the collector. So really, what is the heat coming out of the collector? And the black line you see here is the measured one for these days, so real measurement data within 1 hour resolution. And the colored lines are the output of the forecasting method. You see that this forecasting method is very close to the black line. Here we have some deviation, however, it is still very close. And these forecasted values, actually, you already have available at starting here. So you already know at Tuesday how much heat will your collector produce, and this is a very valuable information to consider this future information in your control strategy. And regarding this Model D forecasting, we also wrote a paper about it. It's open access. You can access it, read it, and apply the method yourself. And I guess the slides will be shared later on, so just click on the link. Then some explanation of Model C. Model C is about the optimal interaction on plant level, so considering everything. And it is focusing on the whole plant, and either by rules or by a model predictive controller, which stands for MPC. And this means, so there has to be a model. So the MPC considers a mathematical model of the whole system. So including thermal storages, heat producers. Then regarding the predictive part, it takes into account forecast data, what will be the future production of solar heat and what will be the future energy demand or heat demand. And it calculates then the optimal operating strategy for a prediction horizon. For example, the next 24 hours based on a cost function. And the cost function can be the overall costs in euro or the CO2 emissions. And in order to develop such an MPC, we first developed different models for the different components of such a system. So we have and programmed them in the program language Julia. It's very similar to Python. So this is only software modules. And we developed models for the gas boiler, for the heat consumer, for the solar collector, for cooling tower, for absorption chiller. And we have modeled this system separately and implemented in software, and in order to have a modular approach, and these models can then be combined to form a model of the whole system. We will see on the next slide. And this model has a certain mathematical structure which has to be used in the MPC and considers, for example, efficiencies, constraints, transport delays. And when we apply an MPC, it is working like that when we come to a system, we have typically the piping and instrumentation diagram, and based on that, based on the real structure of the system, we combine the correct models, and then we will have or come up with a model which represents the whole system and its connections, considering the prices for heat, the prices for gas, the prices for electricity. So we have a simple representation of the whole system which should be controlled. And now I want to quickly introduce you about the procedure of such a model predictive controller. So if we have here the real system, then we will receive the measurement data. First in the ICTs and the information communication and technology infrastructure. So the measurement data has to be collected some way. Then we also receive weather forecasts from a weather service provider. These parts go first in the forecast method module, which I showed you before, in order to calculate the future demand and future yield of the solar heat collectors, of the solar thermal collectors. Then the measurement data is also used to initialize the mathematical model. As said, this mathematical model, so that one which is in here, is a representation of the real systems. And then a certain operating strategy is tried. For example, running the gas boiler at 50% for the next 24 hours. This operating strategy is then varied, is changed so long as until an optimal strategy is found. An optimal in case of a cost function. So we define what is optimal for us, and then a mathematical solver, so a very complex mathematical algorithm, then calculates. This is mathematical optimization, calculates what is necessary to achieve the optimal operating strategy for the system. And this is then sent back to the real plant. And this is done every 15 minutes, and therefore it closes the loop and makes it a control. Yeah. And then at the next 15 minutes, measurement data is received, the mathematical model is initialized, the operating strategy is changed, and when the optimal is found, it sends back the optimal operating strategy for the lowest cost to the real system. Coming now to a short explanation of Model E. This is about distributed learning features. So there we used techniques from the field of artificial intelligence in order to characterize your whole system. So to characterize the different modes which are occurring at the system, and to have a fault detection. So to tell the operator at which part a fault was detected, and that the operator knows when he has to change something. And also regarding that, we published an article in a journal. It's open access, so just click on the link and you can read the whole method, how it is applied, what are the results, and how we used it in order to have an automatic fault detection, fully data-driven. And then coming now to the implementation and the integration of the control tool. So far, I explained to you what is the goal of the control tools: to optimize the operation of a ship plant. Then the design is very flexible in order to be applied at the multiplicity of systems. Then I gave you some explanation to the different modules. And now I want to tell you a little bit about the implementation, how and where it is implemented. So the typical structure that is that we have a programmable logic controller, a PLC, which exists on site at the plant. Then we have an internet connection to a server, to a PC, where the high level control aspects are calculated. And furthermore, we have an internet connection to a front end. So just a browser like Chrome, Firefox, Edge, where you can have an access to these control modules. And the model A and the model B, like controlling the solar thermal plant and the hydraulic integration, they have to be implemented on the PLC, since they have to run in real time. The other modules like C, D, E, and F, like optimal interaction, forecasting, distributed learning features, and calculation of KPIs, are then implemented on a server, and the results can then be accessed over everywhere from your handy, whatever, just accessing the link, the URL over your browser. And now I want to show you the implemented tool. So this is the front end, the part which you can access the control tool over the browser. So you can just put here the URL, then log in. Then you can select a plant. For example, I selected here Roda, a winery in Spain. Then you can scroll down, and for example, you have these different sections. So one is the monitoring part. You can select your plant. You can select a date, like say 1 week before that. Then select a sensor, for example, the solar radiation in watt per square meter, and then you can have access to your data from everywhere. You can furthermore access the forecasting part, then select a date, and here you can see, for example, the solar heat generated for the next days. You can also see the solar radiation for the next days, as well as the ambient temperature. Based on the MPC suggestions, you can go to the plant again, and the MPC, so this model predictive controller, gives you suggestions how to operate your system in order that it is optimally operated. And for example, it recommends you to run in the operation mode for the next time steps called solar boiler caldera, so solar preheating and then using a gas boiler. It also tells you about the storage, the amount of energy you should produce by the boiler, and the state of charge of 2 of the storages which are existing on site. Coming now to the mode detection. This is another feature, so that you as a plant operator knows in which modes your system is running and how often and how much energy is transferred in the different modes. So you can select your plant again, a start and end date, and then can select the mode, put on start, and then you see the different operating modes which are existing in your system. For example, mode 10 means that all the pumps are switched off. This is because it is red. And then you can see how often does such a mode occur. So this is quite interesting. So the switched off mode is occurring 30%, 43% at the time, so likely at the night. Then you also see how much energy is transferred. For example, for the switch off mode, no energy, and you also get some additional information what the time spent in each mode and how much it switches between the different modes. So this was regarding mode detection. Regarding fault detection, it is similar. You have to select your plant. Typically, you can select process plant as well as solar thermal plant. You can select a feature. So in this case, to select the outlet temperature of your solar field, and you can select a certain date, then you put on get, and then you see here, so this is the outlet temperature of the solar collector field, and here these dotted lines are characterizing fault. So here the algorithm found it is faulty that it raises up at such a high temperature, which is actually true, since the solar thermal field should not go up that high, and then you are informed. Coming now to the benefits and the target group. So the benefits of the tool depend really also on the possibilities which are on site. But overall, we can say it should provide you an improved low-level control, so more stable temperature, an improved high-level control to maximize your solar yield and reducing the operating costs, and provide you deeper insights in the plant performance in order that you can, as an operator, can quickly derive the efficiency measures in order to boost the performance. And it can provide you access of your data from everywhere. And the target group, in my perspective, are process operators of ship plants who wants to improve their system, and also technology providers who want to provide an additional digital service. In this case, thank you very much. My name is Victor Unterberger, and if you want to reach out to me, please click on the email, and all the questions I'm happy to answer by mail. Thank you.
Okay, I'm sorry that Victor had to record this video, but this was a very interesting part of the project. If you have any question, we can try to solve that. If not, you can directly contact him. We are going right now to continue with the other tool of the project. Will be presented by Giorgio Bombici from Rina Consulting, which is the replication tool. Thank you, Giorgio.
Thank you very much. So good morning to all of you. My name is Giorgio Bombicini. I am from Rina Consulting, partner of the Ship to Fair project from the beginning, and I am presenting the replication tool. I start by saying that I have not been involved in the development of the replication tool, which was developed by some colleagues at Rina, together with Circe, together with SEA and Lynx. But I am a user of the replication tool, since I will have a second presentation during today's event together with the IRAPWA on the replication studies we have carried out using this tool. So what is the tool about? The tool is about it aims at realizing, giving the possibility to realize pre-feasibility studies for solar heat integration in industrial processes. So the tool is able to map and quantify the availability of heat from solar thermal from different technologies, and the demand, the thermal energy demand of the industrial site, and match them and optimize the technology, size, storage size, and features of the plant according to energy, exergy, environmental, and economic criteria. So the concept behind the tool, this is the concept behind the characterization of the industrial site. So we start from several information regarding the plant, information that are typically collected in energy audit processes. So we start, of course, from energy consumption data from bills and meters for electricity, for gas, and other fuels. Inventory of equipment, basically boilers and other heat pumps and other devices converting input energy vectors into thermal energy with their power, size, efficiency, etc. We add the result of some measurement on site. We carry out analysis, and we come out with the energy breakdown by process, by system, by area, both in monthly terms and at hourly level. More in general, the concept behind the tool is shown in this slide. So we have inputs to the tool that are related to the quantification of the solar resource, so weather data, the surface available. Then we have here all the results of the analysis that they are presented in the previous slide. So basically, the characterization of thermal energy demand of the site, temperature, distribution during the day, during the week, during the year, etc. Then potential storage size, a range of thermal energy storage that could be suitable for the plant, and then the tool carries out optimization. And then we have a wide database already inserted within the tool regarding the performance of the collector, of the thermal energy storage, all the data required for KPI calculation, like standard energy prices, standard emission factors for the different fuels and energy carriers, etc. All of these inputs go into the simulation module, which calculates the performance of the solar field, of the storage, and produces the KPIs related to the proposed solar thermal solutions, and calculates these KPIs related to technical aspects, solar field efficiency, solar share, storage efficiency, then some economical indicators, the levelized cost of heat, payback time, return on investment, cost of stored heat, etc. And of course, environmental indicators like primary energy consumption reduction, greenhouse gas emission reduction, energy return on energy invested, etc. This is the workflow for users using the tool. So starting from, of course, the registration, login, the creation of a new project, the insertion of the data regarding the site, solar mapping module, thermal demand characterization module, simulation module, and integration module, optimization module. And we arrive to the end. So as I have, we lost something here, but as I have introduced, the tool is articulated into 4 different modules. Solar mapping modules, which characterize the solar resource availability, process characterization module, which characterize the thermal energy demand and its distribution during the year, a simulation module, which carries out the simulation of the potential integration of different technologies in the specific industrial plant, and optimization module, which optimize by energy or exergy the hourly production of energy of the solar thermal plant. Now I go into detail with one slide for each of these 4 modules. So we start from the solar mapping module. Here we can see, of course, a screenshot from the tool. The inputs we need to provide are related to the location of industrial site in terms of address or coordinates. Then if we want to optimize, of course, the solar field characterization in terms of available area, if it is an installation on roof or ground, if there are obstacles or shading. If we want, we ask if we want to optimize the azimuth slope of the plant and on which reference years we want to characterize the solar resource. And based on the integration of this tool with the PVG's tool by the JRC, the hourly potential production of 1 square meter of collector or 1 kilowatt in terms of thermal power of solar thermal plant, outputs are produced from this tool. In the process characterization module, on the other hand, we need to input data with reference to the plant. So industrial processes that are realized, a characterization of the thermal energy demand by adding data on the monthly consumption by fuel, the inventory of equipment like boilers, chillers, heat pumps data, the processes that are carried out in the plant with their thermal energy demand in terms of temperature, of fluid, type, daily, weekly, yearly distribution, which you can create hourly by hourly or using this kind of proxy data that are available on the tool itself. In the next steps, in the next part of the tool simulation module, there are common parameters like prices, emission factor, technology features already available in the database, but they can be even customized by the user. You have to provide the thermal storage size range. As you can see, all the results are presented as a function of the storage capacity. So you can say, okay, I want to simulate solution between 0 and 10,000 kilowatt hour of storage. Then you need to provide, to select the technologies from the list of solar thermal technology that you want to simulate, so flat plate, high vacuum flat plate, linear Fresnel, parabolic collectors, and other. And you get as output a lot of different charts, among which the monthly comparison between production and demand, the solar share, some financial parameters like the levelized cost of heat, payback time, return on investment, and the avoided greenhouse gas emission. And then you can go to the integration module, the last one, where you can choose between energy-based, exergy-based, or a mix of the two, and you get as output, among others, the hourly comparison between the thermal energy demand of the site and the potential energy production of the solar thermal plant as a function of the area and the storage, the collectors area and the thermal energy storage that you have from the previous model. Conclusions. This is a really interesting tool for those like me who are carrying out those in industrial private project energy audit, because we typically use Excel. This is a tool that could be available to carry out some more detailed simulations, and it is technology agnostic. So it allows comparing different solar thermal technologies without preferences for one or the other. You need only the basic data on the industrial site to carry out the analysis, the basic data that you typically collect from industrial site in order to carry out an energy audit. So basically, characteristics of the plant, of the boilers and of the process equipment, and their annual, monthly, and if available, hourly energy consumption. The tool includes default values for technical and financial parameters, but it allows you, if you have more detailed data on the site itself, to customize them and get results that are more closer to the specific needs of your industrial site. And then to conclude, the tool provides also some analysis on the optimization of the solar thermal system size as well as of the thermal storage volume, which allows you to quantify all the technical, energy-related, financial and environmental results of the action you are proposing to the industrial site, which in any case is recommended then to go to our technology providers for further analysis before the installation. Practical examples, which is my last slide. In probably 1 hour from now, we will see my second presentation together with Irabua, where we will share with you a practical example of the use of the tool for a replication study that we have done with the project. So thank you very much for your attention, and if you have any question, please ask.
Thank you. So we've seen today the main technologies that we are using in the project, which is the linear Fresnel collectors and also the high vacuum flat plate collectors. We've seen also how we can study the integration of this solar heat into any kind of industry, and also how we can control, even forecast the next days of energy generation, and how we can plan the strategy for our plan to optimize the energy production. And right now, we are going to see the insights from the Spanish use. Yeah. The replication tool is right now limited to the use of the consortium. However, we are exploring to offer that tool for the public audience. So in case that they want to use it, they can contact directly us on our webpage to info@c2fer.com, and we can check if we can offer them that to them. This is something that will be defined in this last month in what we can do for this for the developed software until now. Okay, thank you very much. So finally, Esperanza from Roda will present.
We should see the image of the winery. Well, I hope the rest of the presentation is okay.
So it's easy. The current PowerPoint is that sometimes it doesn't work.
Aquí. Well, I'm Esperanza Tomás, the Iran director from Bodegas Roda, a winery located in Rioja. And I'm going to explain you the other side. Well, the other side of the project. I mean, we are the users of all those technologies that have been explained. We are in the appellation Rioja. This appellation has 60 hectares of vineyard and the influence of three climates, continental, Atlantic, and Mediterranean. Well, I think to understand our participation in Ship to Fair project, you need to know who we are and how we work. We were born in 1987, and we established in the most traditional neighborhood of La Rioja in El Barrio de la Estación, and in our house, in our winery, classicity and modernity merge in order to make a great wine. We want our wines to show the place where they come from, to show the landscape of La Rioja. We are sustainable, all our wines are sustainable. We are characterized by the elegance, and Roda is committed to the R&D as an engine of progress. Starting where everything starts in a winery, the vineyard, we grow our vines in bush vine, which is a traditional viticulture system. We control 120 hectares of vineyard. 80 of them are ours. And also in the vineyard, we do things, we have projects, sustainable projects. For instance, we have a gene bank of 550 clones of Tempranillo that represent all the variability of Tempranillo in La Rioja. And we are in a project that searching for the family of clones better adapted to climate change. We also have a plantation in the key lane system that avoids, saves water and avoids others undesirable effects of climate change. While the R&D is very important in our winery. In this context is born Ship to Fair. And our role in Ship to Fair, we are demosite. We are the users of the technologies that have been or are developed in the project. And why Roda participates in the project? Why do we bring it to the project? Well, we use renewable energy. We use solar thermal energy, not only for heating, but also for cooling, which was a novelty when we were at the beginning of the project. Another very important thing is that the installation, the vacuum tubes should be integrated in the architecture of the winery. We consider the architecture as an expression of the culture of the place. And sustainability is not only about technologies, it's also about preserving our heritage. And of course, we wanted a decrease in energy expenditure. And I would like to say also that from the beginning of the project until now, the situation in the world is changing in terms of energy. Well, we've left the COVID, and afterwards the war in Ukraine, and it's been very important in terms of dealing with energy in industry. Well, here you see the installation integrated with the landscape. Well, and where do you use the heat and the cool? Well, we'll see this in our vinification flux, because I think it's very important for the developers of technology to understand where the heat and the cool is going to be used. Well, we harvest in September, October. In La Rioja, in that period, we have high temperatures. We harvest, and we need to cold soak the grapes at 7 degrees. Then takes place the alcoholic fermentation, which is a spontaneous and exothermic process. Well, in our wineries, it's spontaneous. Other wineries use yeast, and we need also to sometimes to heat a little bit to start the fermentation, and also to cool in order to avoid very high temperatures, because the yeast die and the process stops. Afterwards, the wine undergoes a malolactic fermentation, is November, beginning of December. Then we need a temperature of 19, 20 degrees. In La Rioja, we have 7, 8, 10 degrees. Well, these temperatures are changing because of the global warming, and we need to heat. And afterwards, it starts a process of aging that lasts, let's say, 14, 16 months, and we need a constant temperature of 14 degrees. So in summer, now, we need to cool, and we cool also with the heat obtained in the solar field. And finally, the stabilization, we need 5 degrees. It's a short period before bottling, and we need very low temperatures. And all during the process, we need to clean and disinfect, so we need high temperature. Well, let's have a walk through the wineries to see where those processes take place. Well, the alcoholic fermentation, and well, first of all, the cold soaking of the grapes, and the alcoholic fermentation takes place in all those big vats of 20 hectoliters. And we use wild yeast, so it's spontaneous, the fermentation. Those vats are from French oak, which has a great thermal inertia. Well, the alcoholic fermentation ends, then starts the malolactic fermentation, and takes place in those barrels. Well, in those barrels, and in this building that is 1,200 square meters. So we have to heat it, and we do it with an installed underfloor heating system. And once the malolactic fermentation is finished, we open the windows to the north, so the wind enters, and we cool naturally. We don't need well, after the malolactic fermentation starts the aging period of the wine. That lasts 12, 14, 16 months. And we need to cool in summertime. And we cool through the refreshing floor. So we use the same installation for heating and cooling. We need a temperature of 13, 14 degrees. And well, the last summer, you know the temperatures we have. And now we also have high temperatures. And we also use the energy generated by the solar plant for dehumidifying another cave, well, some other caves, this cave, which is a cave from the 20th century, and we need to dehumidify it, so we also use the heat generated in our solar installation. Well, which were the steps to install this plant? Well, first of all, an engineering visit to know the places, or to put the vacuum tubes or what we needed, and to make the project. Then the permits and documentation. Well, we ordered the equipment, we installed it, and the approval and interconnection. All this process lasted for us approx 1 year. We were very close. Sorry, because we don't see the but and there was an image of the vineyard, very nice. But, well, which were the characteristics of our place? Well, we wanted heat and cooling. The site was La Rioja in Spain, the longitude, latitude, and we needed an absorption chiller to cool. We had available about 100 square meters to put the field. And how was covered our needs until that moment? Well, we had 2 chillers and we had also boilers. Well, sorry, see. Well, here we could see the characteristics of the project to be integrated in Roda. The place we had, we could install it in a rooftop of 100 square meters. Well, it has more than 100 square meters, but that was the space that we wanted to install the plant. We've installed vacuum tubes. The net aperture area was 70 square meters, and we wanted to save 40 tons of CO2. Well, this is just an image of our solar field. You see the vacuum tubes, and well, the primary the fluid of the primary circuit is glycol, and the one of the secondary and tertiary circuit is water. Well, and well, which were our expectations in Ship to Fair project? Why did we participate in the project? Well, there were some cons, some pros. Well, it was a sustainable process. It was a process that was going to improve the energy efficiency of making wine. We wanted, of course, a decrease in our energy expenditure and visibility. And also, we have gained a very well-considered certification in the world of wine is wineries for climate protection. And this project has helped us to gain this certification. But of course, there are some cons, like in all projects. Well, there's an economic disbursement for the investment. Also, there are conceptual difficulties because we are not expert in energies. Sometimes it's difficult to talk. I believe for the energy engineers, it's difficult to talk with us and for us with them. But we always found a meeting point, and finally we understand each other. And also different timings among participants. It's not the same. An industry that needs to use the heat or the cool generated by the solar plant, a developer that has to send a project, or the project will be next month arrives and it will be the other, and it's okay, but the grapes don't wait. And that's important. Well, I don't know. Yeah, it's a pity because the solar field is really nice. Well, if you come to La Rioja, I'm sure you'll come after this presentation. You'll see it in place. It's beautiful. Well, here an example of the solar production in 21 and 22. I mean, the project works. It really works. And well, here is just to summarize the project. Well, you see our winery, you see the solar field. We have 20 vacuum tubes. The total opening area is 65 square meters. The energy produced 60 megawatts hour per year. The saving protein 4,500 kilos per year, and the reduction emission of CO2 30 tons. The solar plant satisfies the 13% of the total energy that we use. Those are the data that we have analyzed in 21 and 22. And well, Again, there was a beautiful image of the vineyard. Thank you very much. If you have any question, you can ask me. As I told you before, I'm not a technician in this area. If I can answer, perfect. If not, I'll send it to our technicians. But here there are a lot of engineers from the project. I'm sure they'll be able to answer you. Thank you.
Thank you very much, Sandra. Sorry for the technical issues. Really encourage you to visit this winery because it's really fun. Also, the environment is really nice. With this last presentation, we finish the first part of this workshop. We continue in 20 minutes at 11 o'clock. If there is any question, yes, feel free to ask. Thank you for your presentation. Sorry for the regarding the achieving timing, what you, let's say, recommend for those partners in future to get this better? For timing based on weight, project is running. With timing for the commissioning, the building.
No, I think for timing of the people.
Yes. Well, all kind of innovation project that has real demonstrators. Fortunately, on paper, the planning always works, but when we face the reality and always talking about innovative technologies, there is sometimes in certain there is issues with the planning, with the timing, also the planning of the administration on the permissions. Usually it changes from country to country. Here in Rhode, I work everything very well, and at the beginning of the project it was running, but the plant in France, we need almost 2 years for them to have the approval of the permissions. So it really changed in all the countries. And our for innovation of projects, we always recommend to start in month 1 to start thinking about the approvals and the installation, because if not, even if the project runs for 4 or 5 years, you will be really in a hurry in the advanced phases of the project. This happens in all kinds of innovative projects, not only on this field. The idea was if we implement European Commission, something like a law, like a so that the condition get shorter and quicker. Could that be yeah, it depends. In other field of project, for example, the ones that are interacting with the electricity grid, it depends also what are the rules, if you can connect an experimental equipment or not. So it's a topic of what needs to change from the European Commission and what approvals you need from the national countries that are in charge of that. So it's a complex question, but well, I believe that the Commission is aware of that, and also we as project planners try always to solve that situation. Okay, so if there is any question, we can quickly chat outside. We have right now a coffee break in the main room, in the main hall, and at 10 o'clock we will continue with Martini Rossi, demo site, and the rest of the presentations of the project. So thank you very much for your attendance, and we hope to see you in 20 minutes. Thank you. Okay, so while the people outside end the coffee break, in order to do not lose the schedule, we will start this second part of this workshop. I hope that the online audience can hear us clear and sound also. So, Again, if anyone new is joining, I'm Miguel Farfuela. I work at CIRFE, and I'm today acting as project coordinator of this project. We have seen the first part of the project. What are we doing? We have presented the replication tool, which serves for traceability studies of any industry with heat demand. We presented also the control tool that aims to know what will be the generation in the next days and in the current day in order to plan the best energy source given the current needs of the plant. And also we know the first-hand experience of Roda, it was the smallest demo site in the project, but also it was very optimized, and we were able to obtain a lot of data from that demo site. In the second part of the workshop, we will start with the Martini Rossi demo plan, 300 kilowatt demo site in Torino. We'll know later about what are the business models and the final schemes for SIP, for solar heat for industrial process installations. And we'll hear from Giorgio again about the 10 replication studies that we have developed in different industries around the world. We'll check the roadmap of the deployment of solar heating for SIP2FAIR, and also the renewable penetration in the Spanish industry. And we'll finalize today's workshop with the lesson learned and policy recommendations of solar heating. So I won't use much more time for the presentation. Just as a recap, this is a 8 million euros project that started in 2018. It's funded by the European Commission, and it comes with 15 partners of European level. I have already explained all of this, so I will give the floor to Antonino from Martini Rossi, who will present by their own experience on installing, commissioning, and also using this solar demonstrator with TVP technology.
Thank
you, Tony.
Thank you, Miguel. Thank you, all of you. Great pleasure to be here. I'm very lucky to be the first one after the break. I'm Antonino Giumure, Engineering Project Manager in Martini Rossi. Today I'm going to introduce you the experience of Martini Rossi as a demo site in the Ship2FAIR project. And today presentation is organized in these 4 main sections. I will start with a brief company description of my company. Then I will focus on the technology used, the one installed in our plant. The third part will be about how this system is integrated into the existing architecture, the existing processes. And I will conclude with the lesson learned and the next steps. So, talking about the Martini Rossi, to introduce it properly, I need to focus on the role of the Pessione Operation Center. The Martini Rossi core of all of its operation are based in Pessione, near the Turin area, that starting from the 1864 has centered his production in this plant. It is considered the cradle of Martini and the producer of flagship brands. And starting from 1993, as the Bacardi Group acquired Martini Rossi, it is also considered a center of excellence not only for vermouths and sparkling wines that are the main products treated by the Martini Rossi, but also the Bacardi bottle. The story of the Martini Rossi started with these three men, Teofilo Sola and Alessandro Martini were 2 of the very first founders. Then Luigi Rossi, the skilled herbalist, joined the team. And as said before, starting from 1864, the operation, the plant moved, the production moved to Pessione for its strategic position, as it is in the middle of the railway connecting Turin with Genoa. And the first one was crucial for deploying and develop the products, the raw materials, whereas Genoa represented the bridge to the exportation abroad. So that's why the production moved to Pessione, and that's why nowadays it remains there. This is how the plant looks like now. I will show you in a few slides again this picture stressing where the main equipment installed thanks to the participation of the project were located. And the plant area is of 161,000 square meters, a covered surface of 68,000 square meters. These are the main data of one of the last fiscal year, the fiscal year 2022. As you can see, the plant produced an overall volume of 19.7 million of 9-liter cases. The 9-liter cases is the most common unit of measure used for building our KPI and also in terms of energy. Here you can see also all the certification gained throughout the years in the environmental field, quality, energy, and also human resources, and the list of all the formulas, recipes produced and deployed in our plant. They can be classified into 3 main categories: the Martini Aperitif, the Martini Vermouths, the Martini Sparkling Wine, and, as said, the Bacardi. But now let's jump to the involvement in the Ship to Fair project. Martini Rossi applied in April 2018 as one of the demo sites. The first months and years also of the project were characterized by a deep activity performed in order to find the best solution in terms of technology provider, technology solution that needed to meet the requirements of the plant, but also the weather condition and the available surfaces where this new equipment had to be installed. In February 2021, the solar field installation was completed, and now we are in the phase, the last months of the project, in which we, after the commissioning of all the system, we are performing the fine-tuning, trying to increase as much as possible the energy efficiency rate of the plant, according also to the plant energy demand. So we are also working, trying to pushing the demand in terms of how many times some processes can be pushed and for how many hours they can last. This is a picture of the plant. Fortunately, here in this presentation you can see at least this picture. So there are also the list of all the main data of the plant. It is made up of 229 high vacuum solar panels with an area of about 600 square meters. And during the most irradiation period, it works between a temperature of 152 degrees and 177 degrees. One of the most important achievement we had during the fine-tuning was to increase the maximum reachable temperature of the system from 165 degrees to 177 degrees. As said before by Miguel, the solar field peak power is about 329 kilowatt. Just a focus on the technology already described very well by Dimitrios during the first part of this workshop. The technology provider is TVP Solar, one of the partners of the consortium. The main feature of these panels is the high degree of vacuum between the external surface and the inlet pipeline. It is able to adapt the energy production based on every kind of external condition, reducing the thermal losses. But as said, during the first months of the project, deep analysis were performed trying to find the best way to use the solar field throughout a typical year. To do that, 2 different operation modes were selected. The winter mode for the period with the lowest irradiation, in which the system works between a temperature of 60 and 120 degrees, heating the environment of the department that stands below the solar roof. Whereas during the summer, we have the aim to produce steam, increasing the maximum reachable temperature of 177 degrees and producing 3.7 bar saturated steam. Going more in technical, this is the P&ID of the system. As you can see, there are a lot of colors and circuits as well. The first one is the circuit 1 in blue, responsible for driving the flow from and to the solar panels. It, during the summer mode, exchanges energy with the circuit in green, the circuit 2, that brings this energy to the indirect steam generator. And in pink, we have the steam generator feed water circuit. I will explain more in details this process in a few slides. Just a quick overview on the thermal block, which is the main side of the system responsible for driving properly the flow. It happens, it is also, here we can see the border between separating the circuit 1 to circuit 2, the main equipment installed, starting with the application, so the unit heaters for the winter mode and the heat exchanger for the summer mode, and the dry cooler, that is a crucial equipment for dissipating the excess of energy in case of emergency or failure, or once the temperature increase above a certain limit. The flow is driven properly thanks to these groups of valves, two-way and three-way valves, all connected with the PLC and driven by the irradiation, temperature, and pressure of the circuit 1. Going back to the P&ID, this is how the circuit 1 works during the winter mode. As you can see, we have in red the hot water exiting the solar panels, fueling the 2 unit heaters that provide heat to the environment, and then coming back to the solar panels. This happens when the circuit 1's temperature is between 60 and 120 degrees. But when the temperature increases above 120 degrees, as said, the flow is driven to the dry cooler to dissipate this excess of energy. This happens during the winter mode. In summer mode, we have now the flow of the circuit 1 driven to the heat exchanger, and here we have a working temperature that stands between 110 and 167 degrees. This energy is exchanged with the circuit 2 that brings and fuel the indirect steam generator, producing 3.7 bar of steam. The indirect steam generator is fed by the water exiting the existing degasser with a temperature of 104 degrees, and this degasser, the integration of the connection from the degasser to the indirect steam generator represent the first example of integration, as the degasser is also responsible for feeding the existing boilers and CHP already installed in our plant. But the water before entering the indirect steam generator, it is preheated by another heat exchanger fueled by the water of the circuit 2 exiting the indirect steam generator. And this is the whole picture of what happens in the summer mode with all these the system itself. Again, the picture of the plant. Here we have the roof where the solar field is installed, and you can see also the department. This department is one of the most important in our plant, since it is responsible for producing for the vermouth production. But the indirect steam generator needed to be installed next to the boiler room. as the steam produced needs to be made available to the existing main collectors, and so reaching all the steam demanding users of the plant. And during the summer months, so when we are able to produce steam, the most important process is the distillation. And this is the department where the pot stills are. So here you can see how having to deal with a 160 years old plant can give us some constraints that produce on our system some inefficiencies. This is another example of integration, the energy architecture made up of the boilers and the CHP producing steam, and now we thanks to the participation in the project, we had the solar field fueled by sun. As you can see, these are also the main categories of the processes that demand such thermal energy. We have the bulk process, as said, the distillation is the most important, the bottling process for the sanification, for example, and then heating the environment during the winter period. Another example of integration from an IT point of view was the developing of this web page that helps us in performing analysis and maintenance, as it is very user-friendly. As you can see, it is easy to see where the flow is driven, if everything is working properly, and there is also evidence of the currently energy production and the overall energy produced since day one of installation. This is a picture of this winter in March. To conclude the lesson learned, I tried to divide them into three main categories. I'm sorry about the graphics of this slide. In any case, the regulatory aspect is the first one, as dealing with the high pressures and temperatures. This system needs to meet some regulatory aspects, requirements imposed by law that are suited for standard solution, for standard technology. There is no specific regulation, at least in Italy, regarding such kind of solar thermal plant. As regards the IT infrastructure, as also seen this morning, the aim of the project is not just to provide the system, but to provide also some tools helping and supporting the integration of these systems. To do that, there is a great amount of data that needs to be exchanged between the partners. Once these IT requirements from the project have to meet the internal requirement of the internal IT department of a big company, this is another aspect to be taken into account. And finally, the mechanical defeats. During a typical day, we can have a difference of temperature between day and night that stands between 130, 150 degrees each day. So it's very stressful for some mechanical components. For this reason, we have had some problems with, for example, some valves, and a deep analysis were performed to find the best solution to solve these, to replace the defective components and to find new solutions that were more adapted to that kind of temperature stressing. Next steps, in 2 words, the fine-tuning. The fine-tuning needs find the best settings possible to increase the energy of such a great number of heat exchange during the different steps of the process. So find the best way of flow rate, opening valves, and so on, to increase the overall efficiency of such a process. And then as regard the IT infrastructure, trying to make it as easy as possible for the supplier to make maintenance and analysis through an adequate IT infrastructure, allowing PVP to enter the solar field in an easy way. All the information provided can be found in the Ship2Fair website, choosing under the section demo, the demo 1, Martini. That's all from my side. There is the thank you missing. I say thank you. And I'm available for questions if
I see that there are some questions. Yes. So where this generated steam is fed to specific block of the brew, is it fed directly at the boiler steam outlet?
Yeah, the process is that we have 3 boilers producing steam at 10 bar, because there are such kind of steam demanding users that need that kind of pressure. For all the others, for example, the distillation, there is a conversion of this steam that is brought to 3.5 bar to a general main collector. With the indirect steam generator, we make this steam available to that kind of main collector. So there is just one main collector that we call low pressure, because it's lower than the 10 bar, and all the steam production systems put them the steam already produced. So we just add a new pipe into the existing main collector.
I think there are 2 heat exchangers and the steam and then you can externally install twice.
Because once this, I can maybe come back to that specific slide. This one. Okay. I think you are referring to this heat exchanger.
So if you go to next slide. And next.
This one.
So you see there is an external heat exchanger in the middle, and then there is a heat exchanger.
Okay, no, that's just trying to simplify this web page. Tries just to simplify this P&ID in order to make it easier for a person from another department, for example, that needs to be aware if everything is going well, because in our company, like also Esperanza said, there are not so many experts in energy. We are a company centered in spirits production. So we needed to build a web page that with a schematic and easy flow chart could make an evidence of error if there is an error to anyone. But yeah, in this case, we just wanted to represent the indirect steam generator producing steam that goes to the pot still. Thank you. Thank you for the question.
Yes. You mentioned this challenge for the regulatory part. This is for open this as a challenge for software. A recommendation also for the definition culture. We express a more emphasize the information. These will all the and we also have faced similar challenges in my market. And when you explain that in person, like you're doing, maybe we have some message that people say because I think it also has to do with the purpose, not only the
yeah. I think there is not so much to do, because it's a matter of taking responsibility. The person in charge of the government to approve your project, he just follow what allow tell him to check and to verify. I think that what we can have as a lesson learned for the projects and so on is trying to be aware of what are the law requirements in terms of standard technologies at the moment. Once we are aware of what the law for the law is mandatory to have for such a kind of system, then we can plan some ways to meet this requirement, but in the design phase. we cannot have this the rise of these problems once the installation is completed, because it's too late. So I think that having the big picture about the law's requirements in each country or region at the preliminary design phase could be very helpful to at least adapt the engineering, the design in a proper phase of the project. Thank you. Thank you for the question.
Okay, thank you, Tony, again. So we'll continue now with the next speaker.
Two speakers, actually.
There will be two speakers, and it will be about business and financial schemes for solar heat. So the floor will be for Dimitris Niragua from TPP and Industrial Solar.
So the two technology providers that are partners in Ship2Fair project will present now together what are the business models that we can apply, or at least we apply as companies and within Ship2Fair to industrial solar thermal projects. And we have split with Rapua the presentation. I will go through some introductory slides concerning the overall market and its prospects. So definitely the market prospects for industrial applications of solar heat are favorable, are positive. We talk about, let's say, the overall policy, but also market-driven factors that favor the introduction and adoption of renewables across the industrial sectors. Solar heat has, over the last decades, presented industrial scale projects and developed the relevant know-how. Costs have decreased for the implementation of the system, although recently with the spikes in the cost of raw materials, this trend may have shifted, hopefully not for long. And of course, there are, as you could see in the previous presentation, there are a lot of different types of applications, processes, and types of integrating solar heat in various industries and industrial processes. There are plenty of funding for the promotion of renewables at European, but not only at global level, and this becomes more and more also driven towards solar thermal. We wish, as a solar thermal industry, that to become even more, let's say, driven to solar heat, because we believe that we can actually make a difference in the short term, because our technologies are already in the market. High fossil fuel prices and these energy security concerns, along with the climate commitments and the Green Deal goals of the European Commission, also provide a boost today and in the future for solar thermal. And these technologies are around for several years. And you can see in this graph that actually, whereas the solar systems for industrial applications have been decreased over the last years, in 2022, in the last year, we see a really impressive increase, and we believe that this can be sustainable in the next years. So the market is changing. There is a dynamic trend towards solar heat. Now, the business models that we apply involve also partners, actors across the value chain of the solar heat. And the whole life cycle of a project, of solar thermal project, starts with the pre-feasibility and the commercial offer, goes through the detailed design and engineering, the actual installation, commissioning, the operation and maintenance, and of course the supply of heat to the client. And in this process, there are industrial partners, the industrial companies that are the potential users, the future users of the solar heat that are involved and they express their interest. There are the companies that supply heat to the customers, which might not be the technology providers. There might be some energy utilities, for instance. There are the public actors or the policymakers that define the regulatory framework. There are the energy consulting companies that the users, the industrial companies can use in order to identify the most suitable solar heat thermal technology for their case. And of course, there are the solar thermal technology providers, the manufacturers, as we are, third-party investors, EPC contractors, so for the engineering, procurement, and construction of the field, but as well as the operation and maintenance services. And just a last slide before I hand it to Irapua from my side. These are more or less the initial phases up to the signing of the contract, the agreement with the client. And it's the discovery, estimate, and feasibility study we were talking about previously. It's the engineering study, so the detailed design and engineering of the field. And then, as long as we agree with the client, we sign a contract, an agreement, which might be different depending on the business model that will be applied.
Thanks, Dimitris. So although business models, they are complex, we try to make it easier for understanding. We have three types that we are focused, and Institute Fair also understood, and there are also publications on that. From that, we have one of them, or the first one, which is the build and handover, which is we call also EPC contract, where the industrial customer, the final user, pays for the system. The contract can also have, or this industrial customer can have an operation maintenance contract with the supplier. We have one which is now becoming even more interesting in the coming years, which is the build and operate. Some people call it ESCO, some people call it heat purchase agreements compared to PPAs. But the idea in this case is that the ship developer, then they invest. So the ship is the solar heat supplier, for example, can be a technology provider, can be a third party. They then invest, implement the plant, and then they basically sell the heat, and the industrial customer buys it. So basically, they have a service agreement, not a turnkey agreement, or not a supply agreement, material supply, merely energy supply. And then we have the hybrid model that in this case, it's similar to this BOT, build and operate, which then the difference is that this system is then transferred, the ownership is transferred after a period of time to the customer, to the industrial customer, and then they operate it afterwards. So basically this is also convenient. We have seen both cases. This is very common for utilities. This is more common for the industry, I would say. Like this system will be operated in a contract for energy supply for 10, 15 years, 20 years. And then afterwards, the ownership is changed from the ship developer to the client. And then the client already has experience over time, so they can basically continue to operate. Normally, these two cases here, they take into consideration that the energy generated by the solar thermal plant is comparable or cheaper than what they have in the conventional heat source, for example, with gas boiler. I will go to a little bit of this example. So this first one is the build and handover. So basically, starts with the industrial customer we need to decarbonize. We were talking before today, what are the conditions? So basically, either they have targets for CO2 reduction, or they have pressing costs of the energy supply. Then there is a contact with the solar thermal supplier, for example. In this case, direct contact here, or via a consultant. Then this, the industrial customer, in this case, as I mentioned, they will pay and invest in this system. They also have the chance to apply. There, for example, in Spain also there were, and there are new calls open for local funding that they can make the project even more favorable. So basically reduce the capex costs. Then the solar thermal plant also can involve and work with consulting plants for the development of the project. Then the project is developed. So there are contracts agreements between here, and the agreement of the supply then is later here to the industrial customer. So the industrial customer came, in this case, it came with the need, and they will take the ownership just after the contract is commissioned. So Dimitris will present here the case that we have in the Ship to Fair.
So we already presented two of those demo sites, the Martini Ross and Roda. There is also a third demo site in Lonaudy, south of France. In all these cases, the technology providers and the contractors have built and demonstrate fine-tuned the systems. There's going to be a transfer of ownership, at least for the two cases in Lonaudy and Martini Rossi, where TVP is involved. In Roda, as far as I know, Roda has already bought the panel, so there won't be any transfer of owners at the end of the project. And what we are trying also to agree with the demo site owners is to have an agreement for post-project support in relation to operation and maintenance services.
Yes, and here's another example. It's a system that we did in 2017 for steam generation. In this case, we built and transferred the ownership from the customer. And we have an O&M support agreement already since 2017. So now for 6 years, this system is in Jordan. So another example, now moving for the second business model, which is the build and operate. In this case, we have the party, which is in this case called ESCO, Energy Service Company. It's a player coming to field, which will then have an agreement with the industrial customer who wants to have the system. The industrial customer before was on this side, now it's on that side. And then this ESCO is actually acting as the middle point between both parts. So the solar thermal supplier or the ship project developer is then having an agreement between this, and this ESCO is having an agreement with the industrial customer. Then, of course, the project is then being developed also with some subcontractors or suppliers. There are, of course, the technical inputs, which is typical even for the previous model. So there are the information of thermal demand, load profile, and so on. But in this case, there is no investment from the industrial customer. Normally these costs are taken by the ESCO. And at the end, where you get all feasibility and engineering, the system is then installed and commissioned. And the good part here is that normally these contracts, it's a performance contract. So as long as heat is produced, it's sold, so the client will only pay for what is generated. There are complications to sign this type of agreement. It's normally a long negotiations because, for example, if the industrial customer has a downtime and the solar plant could produce, how this can be negotiated. So this is all conditions that are put in place in these contracts. It's a more complex contract than, of course, a turnkey. So this contract is more complex than the contract that the ESCO has with the solar thermal. But also, on the other hand, the solar thermal has to guarantee that the system will perform over time. So these agreements also has to be signed at the beginning. This, as I mentioned, is also known as heat purchase agreement. As you are familiar with the PPAs, we are using also the HPAs for heat purchasing. So this is one example from TVP. It's a very nice project.
Yeah, it's one of the largest solar district heating systems, so it's not an industrial application. However, it is really interesting because it's really huge. It's 37 megawatts of peak thermal energy. Its size is 48,000 square meters. And as you can see here, there is the project developer that is involved. There is another company that is investing, and it's the technology provider, TVP Solar, that are investing. In order to somehow agree on between all these partners and the actual user, the district heating operator, we had to establish a special purpose vehicle. That means a separate legal entity which will be responsible for the operation of the system maintenance. And this legal entity has signed an agreement with the client, a 30-year heat purchase agreement. In these cases, which are different from the industrial ones, there is a longer term, let's say, perspective. So it's not 10, 15 years that Rapua mentioned for industrial clients. It's 30-year heat purchase agreement. And the location is in the Groningen region in the Netherlands.
Yes, and then we have the last business model, which is the hybrid. As hybrid because it has part of the heat purchase, but then there's also transfer of ownership, as we saw in the first case. The beginning is similar, we don't go through the same because this beginning is actually the same. The development of the project with the technical inputs also is similar to conventional project and to the second business model. The difference is here at the bottom, where you have the ownership of the system by the ESCO company, or the SPV, for example, in this case, can also be a special entity. This contract normally it's temporary, or shorter temporary, and this, of course, as we mentioned, the solar thermal plants, they operate at least for 25 years. So in this case, if we have a contract of 10 years, as this example here, then the next 15 years, for example, the system will be then operated directly by the industrial client. There is also variations from that. It's always the question of economics. So how long is attractive for the ESCO developer, and how long is it attractive for the industrial client to agree on this contract? So now we go to the funding programs. Dimitris also will continue a bit on that.
I mentioned in the first slide that there is plenty of funding invested from the governments, but also from private investors. And we actually organize the funding sources, public funding sources from at European level, which and we focus in this slide on those programs that are closer to the market. And so the Innovation Fund is one of the major programs that actually invest, the European Union invest on the promotion of renewable energy technologies and applications, and the LIFE program. And there are the national and regional funding programs, subsidies, but also other types of incentives, not only just grants or subsidies, but tax exemptions, loans with low interest rates, feed-in tariffs, etc. And this creates additional incentives for the industrial users to adopt solar thermal applications. Of course, this environment is quite complex, especially if you go to a regional or national level. So it's case specific, but it's something that we would like to stress. For the Innovation Fund, there are four, let's say, areas that are being supported. The production and use of renewable energy is one. Energy storage is focusing mostly, if I remember well, to electricity, but thermal storage is also an issue that Rapua correctly mentioned earlier. Without thermal storage, we cannot reach a high share of solar heat industrial applications. What the Innovation Fund supports is really innovative technologies that are very close to the market. So they are already mature, demonstrated at a smaller scale, and now they will be demonstrated at a larger scale. To my knowledge, until now, only one project was approved that involves solar thermal, and that was in industry, and that was a combination of solar thermal with industrial heat pumps at low temperatures. So we hope that in the future we might have one with our technology or industrial solar technology. So the Innovation Fund has two groups of projects that supports the small scale and large scale. This is under revision. There might be a medium scale category, but still it's under, let's say, discussions. And you can see that there are a lot of funding available. This funding comes from the carbon tax, and can support up to 60% of the capital expenditure of a project. 40% of the grant is distributed after the project has delivered results. So it's somehow the funding is connected with the actual performance of the system. I think this is the last, and for you.
So here we have some national examples. We did not put the funding in the description of the funding because this also changes depending on the authority. These are some examples. If you go to the links, you find the entities that are responsible for that. For example, in Austria, in France, in Germany, in Italy, in Spain. There are also other ones. You can find also some resource in the Ship to Fair project. And we also include the link here from the Task 64, which is focused on solar process heat. They also have made a quite comprehensive list of funding available for research and for implementation of solar thermal applied for the industry. They also try to connect some funds that are available for renewable in general, and these funds can also be applicable for our field here. I think with that, we finish, and we thank you for your attention. Questions?
This answer might sound simple, but it has a very complicated answer. Actually, it depends on the local conditions. So if the cost of energy in a company in, let's say, in France, where there is no connection, for instance, with the natural gas network, might be higher the cost. So the solar heat might be more attractive for them. If there is a company in Greece, for instance, in areas where they use liquid fossil fuels to burn in the boilers, again, this might be more attractive. If you are in, let's say, in the Netherlands, for solar heat, of course, it's not the best conditions because the solar irradiance is quite low, but you might have, in the case of the solar district heating, a rather high tariff for the heat for the district heating network. There might be some other type of incentives, locally available, or regionally available, or nationally available. So things are quite complicated and are based on the local conditions. Generally speaking, the more solar irradiance you have, the better for us, for solar heat. The lower the temperature, the application temperature, the more energy we can produce. That means that we can deliver heat at a lower cost. And the larger the system it is, the more the economies of scale are. So from our side, I think these three main parameters apply mostly. And then there are a lot of small details that might actually make the difference from the client side. Even, for instance, energy security issues or commitments for decarbonization can play an important role, especially in the future concerning decarbonization.
Yeah. I think with that I can complement that also depends on how the industrial customer evaluates these projects. For example, sometimes they want a cost of heat which we call levelized cost of heat over the lifetime of the system, which is cheaper than what they are paying today. This will be a decision criteria. Sometimes they want a solar fraction, and they want to push to get the solar fraction because they have commitments for a certain level. But the most common are not these two. The most common is payback time, and payback time means depends on the investment of the company. Sometimes they are normally the industrial customers, they want the shortest. In some countries they want below 2, some countries below 5, some countries they accept 8 to 10. And these will be then the conditions to calculate that is what Dimitri just mentioned. So you can have, for example, a project in the same country, which in one place or in one company, well, maybe the same kind of system, they could have a payback of 7 years, in another place 3 years, depends on the cost, for example, of energy, alternative energy, and depending if we include funding. Some guys you can include funding one, and the other one you can't. Sometimes even the company, I have talked to companies, they have also their internal carbon taxes. And then they have a tax from the CO2, they include in the calculation. Some other companies, they don't have it, so they are more market-driven, more aggressive in their evaluations. So these are our parameters that we have to evaluate, commercially speaking, should say if it's feasible. But generally speaking, I think I have not seen a case that the LCOA or the system would produce over the lifetime energy that would be more expensive than the conventional sources. So most of the cases we are below. You see some examples from the replication studies. All of them are on the range below the lifetime of the system, which means that the system is feasible. But the decision is not made normally in that case. For example, if the payback is 21 years, they won't take the decision to install, unfortunately. Although the system could deliver for even 4 years more, and nobody knows how will be the energy costs next year or in 15 years. But these are, yeah.
So what I can also add here is that the business model also plays an important role. So if someone wishes to have a payback period of 5 years with a CapEx model, the payback period is 10 years, then you might try to work on a heat purchase agreement if the levelized cost of energy of heat is lower than the actual cost of heat that they pay. And you might, let's say, end up with a levelized cost of, let's say, 40 euro per megawatt hour, and your still may not be, let's say, attractive to a company that operates in Egypt, for instance, because they have very cheap natural gas there, or to India because they use coal. Mm-hmm. So we cannot compete with coal in terms of energy alone. And you can have as high as 70 or 80 euro per megawatt hour and still be competitive because the local cost of fossil fuel, using fossil fuel for heating are higher. So it depends a lot.
Okay, thank you very much, Dimitris and Irapua. We'll move right now with Giorgio's contribution and Irapua also. We'll learn about the 10 feasibility studies of the project. I will continue also the topic that you have been discussing right now. We are running a little bit out of time, but we hope with what we have. Thank you very much.
Thank you, Miguel. And it's really nice to start after this discussion on what impacts on the profitability of solar thermal solutions, because here in this presentation at the end you will see the results of the 10 case studies we have carried out, and we can make together some comparison regarding different sites in terms of size of thermal energy demand, of baseline energy production systems, etc. So we have presented here the results of the replication studies we have done within the Ship2Fair project using the Ship2Fair tool that I have presented earlier today. We are talking about 10 industrial sites belonging to 8 different industrial sectors. Textile, we have 2 companies. Chemical, we have 2 companies. Wastewater treatment, dairy, meat curing, brewery, food, and laboratory. Laboratory, the mechatronic field. These sites are located in 6 countries: Italy, Spain, France, Slovenia, Jordan, and India. and they have a heat demand between 30 degrees and 195 degrees, so quite a wide range. You can see on the map the countries we are covering. The scope of the pre-feasibility studies was to carry out a preliminary analysis of the potential for the integration of solar heat in several industrial processes. We have done, as I have mentioned, this replication study, this pre-feasibility study using the tool. We have discussed the result with the beneficiaries of these studies and fine-tune the result to evaluate the suitability of these for each case. We have been in direct contact with our technology providers here to proceed with further studies, and we have discussed the result before publishing the report. The report will be available on the website now at the end of the project, and will not include the name of the companies and will protect confidential data, because we have this request from almost all the companies we dealt with not to publish the data with the name, since they consider the data they have provided regarding their plant, energy consumption, etc., to be confidential. But of course, we have the full replication study delivered to them, and then the public version of the studies that will be available online. Just a quick reference to the previous presentation. So we have done for each replication study the analysis of with the solar mapping module, with the industrial process characterization module, with the simulation module, and evaluated the integration of the solar thermal, heat from solar thermal with the specific industrial process. Now I leave the floor to Irapa for the presentation of one of these studies, and then I will come back for the comparison of the 10 application studies and the lessons learned from this.
Thanks, Giorgio, and I hope you don't get bored of seeing me so often here. I will try to make this case quick because we had made several. Industrial Solar contributed with 3 of the cases. All of them are interesting, and I think the tool is very user-friendly in a way that it makes easier the life of who wants to at least select which options are available and which KPIs can be drawn. We started in this case, we showed this case, which is also really relevant for the audience here, which was a case in Spain, in Tarragona. The company is a chemical plant with the main products industrial cleaners, personal care products, and emulsionants. The heat supply, in their case, they are connected to the natural gas grid. They have a 4 megawatt boiler there. A bit strange here, but okay. They have several processes, and as most chemical plants, they operate 24/7. We analyzed the process that works at 195 degrees Celsius with steam at 13 bar, which is what we call like medium pressure steam. The annual demand of this plant is, looking at this part, is above 13 gigawatt hours, and the annual associated CO2 emissions is above 2,400 tons of CO2. So as Giorgio mentioned, so in the solar mapping module took the irradiation database that the Ship2 replication tool has behind. So then you can see what are the direct normal radiance and the global in-plane radiance for the location. There's also other parameters. We also showed here the ambient temperature that was also taken from the database. This is also used for this calculation of the performance, the thermal performance of the technologies that are simulated. The thermal demand, then of course, in this case, as mentioned, we have the input of the monthly value of the demand on this plant, and also the inputs on the hourly and weekly, daily load profile. As you can see here, you see the load profile over the year. In this case, the weeks are clustered here. As you can see, there are, although it looks like there is a very big gap here, but it's only from 1,400 to 1,600 because the scale is starting at 1,300 here. One of the main boundaries, as always, the solar thermal systems, they need to set an area limitation. In this case, they have ground area of above 26,000 square meters. We selected technologies that could deliver heat in this range, as we mentioned, between 100 and 200 degrees Celsius. So in this case, the flat plate collectors are not included. And this is the area, the collector aperture area that the replication tool already has the parameters of conversion how much collectors you could fit using this area. Of course, this also can be adapted because we took like a rule of thumb, like what the tool does. You could also adjust that individually if you are more into every technology. And this is an interesting result already, which is the result of the simulation module. The graphs show the different colors of what the collectors would produce. Basically, you see the graphs from the months, and the orange is the demand, and the other parts are the technologies, how much they would produce over the months. This is done also as an analysis because this data is also later used for the other KPIs. Then we start with the part of the sensitivity analysis, which in this case starts with the storage. Then in this case, the storage shows basically that the solar share increases when you increase the storage because you can use more of the energy produced. You can see basically the trend for all the technologies. The second parameter, or important, there are others, but one of the most important parameters is the levelized cost of heat. As you can see, the levelized cost of heat also, in this case, compared to the storage, reduces, which means it gets cheaper when you can store and use energy outside the sunny hours, let's say. And one another important parameter, as we mentioned already, is the payback time. In this case, is one case that the natural gas price, as I mentioned before, it's cheap. They are connected to the grid, they are chemical plants. They have very good contracts for sure. And then I'll see that the levelized cost of heat ranges from 30 to 60 years, which of course is outside the lifetime of the system. But when you go to the large storages, it will still be possible to match their expectations on the lifetime of a solar thermal collector. The CO2 emission reduction also has a relationship with the storage that improves, of course. If you have a large storage, it means that you use more energy, you reduce the CO2 emissions from the fossil fuel. And then George will show and comment more on the other studies, which is then summarized.
Thank you, Rafa. Thank you. And so we move to the discussion on the 10 replication studies. Here you can see a table summarizing the results of the 10 replication studies. So you can see the industrial sector and location for each, the thermal demand temperature, the best technology selected as a result of the replication study, the collector's area, levelized cost of heat, payback time, solar share, and greenhouse gas emissions avoided. As you can see, we can already see, looking at the table, some of the effects that Irapo has mentioned, looking at his one of the 3 replication studies he has done. We can see that, for example, linear Fresnel reflectors and high vacuum flat plate collectors are the most recurring technologies in terms of best suitability for the industrial site we have considered. We can see that we covered quite a wide range of collectors area based on the space available from on the industrial site, which was in most cases the limiting factor, as already anticipated by Irapo. And the case we have seen for the chemical industry in Tarragona was one of the most suitable cases in terms of solar share, because you could reach more than 50% of, you could cover with solar thermal heat more than 50% of the thermal energy demand, which was one of the highest levels reached in this replication study, since in many cases the limited space available was leading to a very low solar share, around 5 or in many cases below 10%. In terms of levelized cost of heat, the main influencing factors are the technology selected and their operation and maintenance costs, especially related also to integration with thermal energy storage. The payback time, on the other hand, is strongly influenced by the baseline energy production system. So you can see that plants having cheap thermal energy supply, for example, with good contract with natural gas supply, have a longer payback time, while on the other hand, for more expensive heat production system in the baseline situation, you get a better payback time in for solar thermal solution. And then the greenhouse gas emissions avoided are the result of the primary energy demand of the site and of how much we are able to cover that demand with solar thermal solution. It is interesting to see, for example, the last row of this standard application study, which is in India, using coal in the baseline situation. You can see, although we are covering only 4% of their thermal energy demand with solar thermal, we are achieving a reduction of CO2 emission by 7,000 tons per year, because they are using coal with much higher greenhouse gas emission factor than natural gas. We have some additional conclusions here. I think I've already mentioned, looking at the table, most of them. Okay, so high vacuum flat plate collector are among these replication studies the most suitable technology for thermal energy demand, slightly below 100 degrees in our cases. Of course, we can reach even higher levels. While on the other hand, linear phase reactors, reflectors, were the most suitable solution for site with higher temperature in thermal energy demand. In most cases, the limiting factor is space availability, as I have mentioned, and I have also mentioned the conclusion of the avoided greenhouse gas emissions. So I move to the last slide on lessons learned, which is more related to financial aspects, where I would like to mention that levelized cost of heat and investment payback time are strongly variable from one case to the other, as you have seen. The main influencing factor is the ratio between the initial investment you require for the installation of the solar thermal plant and the thermal energy production of the site during the year, which is based on availability of solar resource, on the potential for integrating in the same time, using eventually, in case, the thermal energy storage, the production with the heat demand and consumption. On the other hand, they are influenced, especially the payback time, by the baseline thermal energy production cost, which depends on the type of fuel, price of fuel, as well as on the efficiency of the boilers and other thermal energy production systems that are used. I would like to mention that all of these studies were done considering the normal fuel prices before the energy crisis in 2022, since considering natural gas prices of 200 or 300 euro per megawatt hour, definitely this value would have been better in financial terms, which is connected to the strong increase of the market for solar thermal technologies last year that was mentioned earlier by our colleagues. Moreover, I also highlighted that no public incentives was considered in the evaluation of the profitability of this solution in the replication study, which could contribute significantly as well to the reduction of payback time, basically. And to conclude, carrying out these application studies on external companies of such wide range of industrial sectors and countries worldwide has demonstrated that there is really the potential for solar thermal to cover a good share of the thermal energy demand in all the industrial sectors that have a significant thermal energy demand, provided that site-specific prerequisites are met, like, of course, solar resource availability, depending, of course, on the latitude, but also on more local conditions, like orientation, slope, obstacles, shading, etc., and availability of space, which we have seen is a limiting factor in most cases. Thank you for your attention. And
thank you very much, both of you. I believe that the table with the 10 use cases is one of the most important outputs of the project. You can compare different situations in this. I don't know if there is any question from the audience or online. If not, no? Okay, thank you. So I will give the floor to Nicola Chiara from Links that will present the roadmap of deployment of of the solar heating for industrial processes.
Thank you.
So the floor is yours. Thank you very much.
Thank you. Hello, everyone. My name is Nicola Chiara from Links Foundation. I'm an innovation and business analyst, and I'm here to introduce you results from the activities related to roadmap to deploy the solar heating for industrial processing within Ship2Fair. The main objective of this task were the following ones. So, tailor the project result to the most promising use cases, identify and analyze the barriers, and present a possible roadmap of the replicability of the ship-to-fair in other industrial sectors. We will analyze each of them and finally have some consideration regarding the objective and the results related to them. At first, we start with the most promising use cases. So based on the experience gained in both control tool and replication tool implementation, the commissioning phase, and all the integration and demo sites activities, it emerged that the solution more suited in ship-to-fair was the one related to the use that require cooling and heating with water in their processes. So the target market is related to the industrial sector with process temperature in between the range of 50 and 250 Celsius degree. And the identified sectors that satisfies this condition are these ones, so food and beverage, transport equipment, textile, machinery, pulp and paper industries, and chemical industries. And of course, the most promising use cases would also be the one that utilizes the solution, the technology solution based on the one developed within the project. So vacuum tube solar thermal technology for process heating and cooling, high vacuum flat panel for space heating during weekend period and process heating during summer period, and finally high vacuum flat panel technology for boiler preheating and process heat. Talking about barriers, I would like to highlight three main barriers that we encountered during the process, the project work. First is regulation compliance, because each country had unique characteristics and in terms of regulation compliance, and this issue caused delay during commissioning phase, so it is a potential barrier to deal with. Second, the implementation of control tool and replication tool revealed that in order to interact properly with the tool, it is necessary to speak in English correctly. And moreover, the scalability analysis developed on the tool revealed that having a specific technical expertise in the energy sector is important to interact with the tool. So this makes even more important to include multi-language interface in the tool to facilitate the replication activities and scale up of the ship-to-fair solution. The third barrier that I would like to highlight is related to the lack of specialized personnel. Project experience revealed that the type of ship integration chosen may affect the complexity of the final energy system, its management, and also the required learning curves. So this leads to this barrier in replicate and scale up the solution, because it's difficult to find specialized personnel in the energy sector and in the solar sector with these small, medium enterprises today. There is also another related barriers in this field, and it's the lack to find small and medium enterprises with a proper IT internal department. This is essential because to properly interact with the control tool, an IT department is very important, and otherwise it's challenging to deal with this stuff. The final objective is related to a deployment roadmap proposal. Here, a scheme, a sort of Gantt chart representing the proposed roadmap. As previously discussed, regulation compliance is a key aspect. So it's strongly recommended to start dealing with this activity right from the start, so from month one. Regulation compliance deal with both regulatory and environmental authorization, as well as construction permits. And immediately after regulation compliance, it's important to start with design phase. So all the engineering and system integration activities that are involved in the process. There is a bit of delay with regulation compliance because in the early stages, regulation compliance may produce some, let's say, constraint parameters to the design phase. So this is why there is a little bit of delay in design phase starts. Then we have the activities related to the replication tool that are independent from the physical new sites. This is why they can be deployed right in parallel with the design phase. And then we have the local business ecosystem development. This is a really important aspect, and I will highlight it also in the conclusion, because the creation of a local value chain can be started from the solar energy provider involved in the project, but it's related to a lot of different players and characters in this activity. So engineering and construction companies in the region where the new ship site is developing needs to be selected, and on their side, those companies needs to select the installer and local installers and local suppliers of energy equipment. This is fundamental because without a consolidated and efficient local value chain or local business ecosystem, it's not easy to have a fast and efficient installation commissioning phase that is the immediately following phase. Here, logistic is a key aspect, obviously, so it's important that this value chain is able to guarantee logistic and components procurement on time, not to delay the system installation and commissioning. When the new demo site is running, control tool can be developed. Here, as well as for replication tool, multi-language development and testing can take place. We also have some activities related to the communication protocol development and testing and the MPC development and testing. These are important because communication protocols have to be in position to make the interaction between the internal network of the demo site and the control tool infrastructure working. And also MPC development and testing is important because this ensures to target the MPC to achieve the desired KPI of the new demo sites. Last but not least, training. This is also a very important activity because facility personnel must be trained to interact with the ship plants, and so the training can start in parallel with installation and commissioning phase, just to reaching as fast as possible this goal. Have to be performed this activity to pay attention to both theory and practical aspects to ensure the possibility to act quickly both on a standard procedure and emergency procedure. So, for example, to manage a failure. And finally, some conclusion. Ship2Fair developed and demonstrates a set of tools and methods for the development of industrial solar heat project. To effectively replicate and scale up the solution, several aspects are key. I would like to highlight two of them here. At first, the collaboration of the actors involved in the Ship2Fair experience have generated a new knowledge that can evolve in the future to form those local value chains we discussed before on the roadmap on application of solar heat for industrial processes. And this is an important aspect also to widen the adoption of solar thermal at industrial scale. Second aspect is related to training activities because ship is still a nascent market. So few innovators and early adopters have already installed ship application. And so for this reason, know-how on the installation, integration and commissioning activities is not well distributed, let's say, on the market. So it's hard to found. It's difficult to find this at local level. So to fill this gap, training activities on each new ship plants will be key to effectively and to effectively replicate ship-to-fair solution, it's important that staff training is supported by a sort of comprehensive guidebook, something that include operation and maintenance standard procedures with all the working instructions that cover the different aspects related to the integrated energy system involved in the process. So I think that's it. I would like to thank you for your attention, and I remain at your disposal for any doubts or clarification regarding the proposed roadmap. Thank you.
Thank you very much, Nicola. Just linking your last words on the Ship2Fair webpage, we have some training toolkit with some basic information on all of the project, but also on how to design a solar plant. So you can find over there all the modules of this training capability program that is available there, and also you can find also all the public deliverables available of the project. Thank you, Nicola.
Thank you.
Final presentation before the conclusions will be the one presented by Susana, who will be the renewable penetration at the Spanish industry. Susana came from Cooperativas Agroalimentarias. The floor is yours. Thank you.
Thank you so much. As Miguel told before, I'm working in Cooperativas Agroalimentarias de España, which is the organization representing the cooperative movement, and I'm going to present our organization later. Well, just to have in mind some topics to ambience the presentation. You know that we have an European goal about climate neutrality by 2050. In Spain, we have to turn to the decarbonization of the economy with a stable strategic framework, legislative term. We have three main legislative packets like climate change law, integrated national energy and climate plan, and also the fair transition strategy about the integration national strategy and climate plan, the PNIEC in Spanish. We have information about this plan, which was approved in 2019, and the following results are expected to be achieved in terms of 21% of reduction in greenhouse gas emissions, but also in terms of renewable energy, we have to follow initiatives and activities tending to a significant growth in the penetration of renewable energies in Spain, which is 74% in electricity. Now we are at 51% more or less, and 42% in the use by 2030. So we are on the way, but we should improve in the coming years just to go to the final goal of this plan. And at the end, we have to achieve 39.6% of improvement in energy efficiency. In that sense, we know that the industrial sector is, after transport, the sector that consumes the most energy in Spain. We also know that the immediate energy demands with a high thermal component is the typical situation. So we need to change, the industry needs to change. In that sense, the decarbonized circular and more sustainable economy model is needed, and also a greater weight on renewables energy. So in that sense, we know that Spain ranks the eighth in the investment in renewables, but we need to go further. After this first analysis, in our organization, through our participation in Ship2Fair project, we would like to know about what is happening in the agri-food cooperatives. In that sense, we are representing around 4,000 cooperatives in Spain, owned by more than 1 million producers or farmers, and sourcing
of more than 100,000 employees. And for knowing what is happening in agri-food cooperatives, we have done a survey. We have surveyed our cooperative. We have sampled cooperatives from almost all the regions in Spain, and we have obtained answers from most of the sector, agri-food sectors operating in these cooperatives. After this first analysis, we have the data from yesterday, but we are going to continue gathering data to make a deeper analysis in the future. But from yesterday, we have this answer. We have obtained very various answers in terms of size of these cooperatives. They are some small cooperatives, but also bigger cooperatives in terms of annual energy consumption. So it's very wide the range. But we have interesting answers in terms of the green energy certified supplier. That we have information about the almost 20% have green energy certified suppliers. More than 50% are using renewable energy, have installed this kind of technologies, which is very important for us. In terms of percentage of energy used from renewable sources, we have the information that between 20 and 40% of this energy is used. And from the overall view of the answer, in terms of the cooperatives that have answered this survey, most of them have declared that the installation that they have is solar photovoltaic, less have biomass, and in the third position is the biomass production. So you know that the agri-food sector is very rich in terms of providing biomass. And in the fourth position is the solar thermal energy, the biogas, and the other technologies. Speaking about each of these technologies, we have the data, but we need to refine and also to check the results overall in the total installed capacity and the annual generation, since we have to review the quality of this data. But now we can present the preliminary assessment of this data. So in that sense, we have the solar thermal energy information. The only a very small sample has declared that have this kind of installation, but in that sense, we have a couple of ideas or several ideas about how can focus this installation. The total installed capacity is an average of 28 kilowatts. The annual generation is an average of 29,000 kilowatts per hour. Most of the installations are owned by the cooperatives. The main use that they have declared are cooling, drying, hot water, and sterilization, even pre-cooling, so preheating. And the average temperature obtained is 90 degrees. All of them are on the roof, an average of 100 square meters, and the technology declared is flat plate collector. In terms of photovoltaic energy, the total installed capacity is between 20 and 2,500 kilowatts. The annual generation, the bigger declare is 2.5 million of kilowatts per hour. Most of the installations are owned by cooperatives, and 88% use this kind of energy for self-consumption, and only 12% of these cooperatives use this energy to the grid. In self-consumptions, they use for refrigeration, for air conditioning, for drying, pre-cooling, dehydrating, in terms of using for the cereal, for example. The discharge is to the grid in 32%. Are on the roof, And they are using an average area of 2,150 square meters and until max of 40,000 square meters. In biomass consumption is very typical in the agro-food sector or in the olive oil mills, since they are producing their own biomass, so they are used to be aware of this biomass consumption, and they are obtaining strong benefits in terms of economic, but also environmental benefits. They have a total installed capacity of 400 to 1,000 kilowatts, annual generation of until 16,000 kilowatts per hour. They are the owners of the installation in most of the cases. They are using the biomass for heating in most of the cases. For some processes usual in this kind of industries, which is drying, heating, also in the case of olive oil, heating of installation, and so on. And with less importance, but with a lot of necessity for the agro-food sector, so we think that is coming a kind of revolution in renewable energy. Other cooperatives are using biogas and aerothermia, and a big sample are producing biomass from olive pits, olive pomace, grape seeds, pruning, etc. They are producing an average of 1,000 tons. They are self-consuming this kind of biomass and even sell. For example, in the case of olive peat, is a good fuel, and they are also selling this. And just to have overall ideas about that we have obtained in this answer of this question, only 30% have carried out an energy audit, but around 50% have implemented energy efficiency measures. They are convinced that they need to go ahead with their renewable energies. Between 50 and 60% have interest in energy communities, have interest in agrovoltaics, considers that the cooperative should be a promoter of the deployment of the both kind of technology, but also the rest of technologies. And in the near future, what we are going to see in the future that 66% intend to expand their capacity in renewable energies or make use of other renewable technologies in the near future, from now to 3 years. And about the technology to install, we have obtained this answer. Most of them, 80%, are thinking about solar photovoltaic, but the good news is that 11% are thinking about solar thermal energy, because I know that they are very interested in this kind of technology, since we have surveyed in the Sea2Fair frame, not now, but even in the proposal of the project, but they are convinced that the solar thermal energy is very useful, but now they think that it's difficult, that we are seeing today, but it should be in their eyes, I think. The biogas, etc. So that's all from my side. Thank you so much. You have my contact there.
Thank you very much, Susana. It's really interesting to know how Spain is moving in that sector into renewable production and its integration in the processes.
I have one question. I have this the US and also by solar thermal.
Sorry, I can't hear you.
I've seen that.
Yes, I think so. But I think that the complexity of the system is one of the the things that they are they have stopped the decision, and also the prices, because in fact, as you know, the photovoltaic is well developed in Spain, the rest of Europe, I think, and relatively is simplest in the installation and the maintenance and achieving the main goals. And I think that in the case of the solar thermal energy, it's going to be in the same way in the coming years. But now it's still difficult to think about this kind of installation. But even having this information, the interest is very, very hard in the case of cooperatives. Since when we prepared the proposal of Shift to Fair, a lot of them, for example, in the dairy sector and the concentrated tomato, were very interested in the project, but at the end they decided not to go inside of the project because of the prices, I think, of this technology. So, but I think it's like in any kind of technology, this technology needs evolution to be understood by the people, I think. So, but the interest is here, so it's a good news.
We have installed solar photovoltaic, and we also have biomass with the occupants. And the solar thermal is very interesting when you only need hot water, but I think, that's my personal view, it's not so well developed as the solar thermovoltaic for the complete process of working of a company. There are too many difficulties, and there are, well, I think that a lot of you are engineers of energy, and I think it's it's something interesting to develop and to it's a name perhaps, but at this moment my feeling as a user of the three technologies is that it's a little bit less developed, and this project has been very important to develop still a little bit more. For a small medium companies it's difficult. All the examples I've seen from you and from TVP are big companies in, I don't know, in Arabia and but in Europe we have a lot of small medium companies, and sometimes it's too difficult to install a solar thermal installation comparing to the others.
Yeah, this is a common conclusion of this technology, that integration is complex, that for huge demand and big companies can make sense, but for small demands it's really complicated to integrate, at least as it is today, for now.
We are confident for the future.
We are reaching the end of the session. More questions?
Is in this market, in Spain, available area a restriction or not? But if it is not a restriction, you might go to that. But if it is a restriction, then you need to be a restriction.
There is common, if you travel around Europe, it's common to say that in Spain we have sun, we have wind, and we have also the space to use it. So this is an advantage for other regions in which it's more complicated to use the available land, or that there is not that available space. And here we have the lucky that we have the resource and also the land, I believe.
For example, there are space for there is no problem.
Okay, so just for the conclusion, we have Luis Perez, director of FIRFE, that just will comment on the highlights of the project, and it will be the last speaker of today. Thank you. So the floor is yours, Luis.
Yeah, okay, I'll try to be really short because we are all hungry. So I happen to be the technical coordinator of Fair for these very last months. So, well, that places me in that situation where I have to close and start the conclusions of this project, but please give all the credit and all the gratitude to the people that speak before me and which has been pushing towards the success of this project. So I wanted to start thanking saying thanks to the organization of the Sustainable Places event, to all the speakers again, and to all the audience who choose this session, because there were a lot of interesting parallel sessions at the same time. Then, well, Sip2 Fair has been a really long trip and not the easiest one, to say, but it also has been, I think that we can have this sense of accomplishment, and we extract a lot of learnings as we have witnessed during this session. And we also had the chance to hear it from Roda and from Martini, which explained how they felt about this project and how it integrated in their processes. I wanted to highlight Esperanza talking about this experience integrating the technologies and tools and the importance of adapting to each process, because that's really key when you have to integrate it. Sorry? No, it's not a presentation. So she talked about the importance of adapting the heat that you produce in the optimized process or aspect of your industrial processes, which is really different from one industry to another. So for me, that's one of the keys, and that we have to solve also. Then Tony talked about another really important aspect when we talk about agro-industry, which is seasonality. And they managed to adapt their solution to a winter mode and a summer mode, which is quite interesting and quite replicable in some other industrial processes related with food, beverage, and agro. And then he introduced also the aspect of a lack of regulatory aspect at a national level, which is also one of the barriers for this and some other developing technologies. It's not new, but we will have to deal with that also. Then, well, from our point of view, from Circe's point of view, it has been a pleasure to have such a consortium and have bringing together researchers, engineers, industrial partners. As you have seen, Sip2 Fair has a lot of numbers, a lot of different, more technical approaches, more business approaches, and so on. But I wanted to express my gratitude for the work to the more technical part, especially Victor, who demonstrated from his video the importance of having people enthusiastic about control and the importance of the control systems, and how it's quite hard to explain and to understand for most of us, but it's also a key part of this project. Then Giorgio and Nicholas explained a lot of the roadmap and the main barriers. We discussed about the differences between technologies, the Fresnel, the solar vacuum panels, and so on. That's also really important, and I think we have seen a lot of progress also in that area during these years. Then finally, we had this interesting debate about the natural gas during the coffee break and at some part of the session. And well, that's really interesting, and that give an extra push towards the decarbonization. But we will also have to keep making efforts on regulations and trying to adapt to the goals that the European Union has set for the different industrial processes. Susana summarized it really well, the situation in the agro industry, and also enlightened the use of different technologies, because, well, decarbonizing not only the agro industrial but also the industrial processes around Europe is a hell of a challenge, and we will have to deal with that. We using solar heating, using biomass, using hydrogen, and whatever. So I think that Sip2 Fair gave us the opportunity to give a great push to solar heating in industrial processes, but we also have to learn from the rest of the event, and I invite you to do so. And thanks for being, well, trying to challenge these barriers of decarbonization of industrial processes. So thank you all and enjoy the rest of the event.